as a part of APGENCO 2025 preparation, my current video is regarding the mutual inductance. Above topics are discussed in my earlier videos. You can watch them. Now going on to mutual inductance element. Mutual inductance. It is the property by which the current in one coil produces a flux that links with the other coil and resulting in generation of EMF. This property is called mutual induction. As we know, the voltage equation, induced voltage equation, E is equal to N d phi by dt. As it is an secondary term, so it is N2. From this equation, if you divide by current on numerator and denominator, we will get this term as mutual inductance. By this formula, we can tell mutual inductance as flux linkage of a coil per ampere current in another coil. The flux linked in this coil by the current flowing in the other coil. That is the definition of mutual inductance. Mutual inductance is equal to the ratio of flux linkage in coil 2 by current in the coil 1. Expression of a mutual inductance. We know from self-inductance N1 for this coil, the mutual inductance will be coming from the basic self-inductance, that is N1 phi1 by I1. For coil 2, the self-inductance is N2 phi2 by I2. The mutual inductance will be N2 phi1 to the flux generated by first coil, which is linking to the next coil, that one by the first coil current. The term come across in this topic is coefficient of coupling, K. The coefficient of coupling is the flux from one coil that links the other coil divided by that the flux of same coil. You can see K is equal to phi 1 2, that which links the other coil due to coil 1, that is phi 1 2 by phi 1. If the total flux phi 1 which is generated from coil 1 directly equally links with the other coil, then the value of phi 1 2 equal to phi 1. So that time the K value will becomes 1. That is without losses. Another term here, if there is a property that if coil 1 generates flux that links the other coil and it generates a current, that current also produces one phi 2 that also links with the first coil. That is expressed as phi 21 by phi 2. And if we rewrite this equation, phi 1 2 is equal to K times of phi 1, phi 21 is equal to K times of phi 2. And substituting in equation M, that means earlier we saw phi M will be N2 phi 1 2 by I1. We know phi 1 2 will is equal to K times of phi 1. M is equal to N2 phi 1 2 by I1, and the current which is linking from phi 1 to that means from coil 2 to coil 1 is this one. And if you substitute the values, it looks like this. And from the self-inductance equation, we know L1 and L2. If we multiply both M, then it will become M square. And if we take common L1, L2, it becomes and K square. And M the final equation, the other coil, and if entire flux links with the other coil, then the K value is 1. If K value is 1, then it is tightly coupled. If K value is fractional, it is loosely coupled. Dot convention is used for mutual inductance calculations. There are two rules. First rule is, if a current enters a dot in one coil, then the mutually induced voltage in another coil is positive at the dotted end. This means, consider a circuit. This circuit, the dot is at the beginning. Here also the dot is at the beginning. If the current enters to the inductor through this dot, then it is called entering. If the dot is placed after the inductor, then the current leaving that inductor through this dot, then this is called leaving time. This is entering time. If the current enters into the dotted inductor, then the coupled circuit coil, the dotted terminal will be signed with positive. As here in this circuit, the current is entering, so the coupled coil 2, the dotted portion is assigned with positive value. Similarly for the rule 2 also. Here, as the current entering, the voltage equation on this circuit is written like this. For a clear explanation, the same circuit drawn here, but in this is converted into an voltage drop is, mutual inductance voltage drop is shown here. As the same L1 is drawn here, the mutual inductance between this is, there are two, for every coil there will be a mutual inductance. If this flux connects to this flux, then this produces one mutual inductance drop, and this flux also connects to this coil and produces one mutual inductance voltage drop. So that is shown here. This is the current I1 current flowing into L1, and here the voltage drop, this is due to current flowing from the second coil. So that's why it is written as M di2 by dt. Here it is the similar circuit with I1 current which is flowing in the coil 1, M di by dt. So this positive sign is given because the current entering here, so the dotted terminal of the next circuit will be positively assigned. So at the starting it will be positive. So here also the effect, so it is positively written. So when we looking from this, the I2 current is entering into the dot. That means the coupled coil 1, the dotted portion will be positively assigned. So in the front of inductor, it is a positively assigned. So the drop is positively given. So if you apply a KVL here, input voltage is V1. So V1 L1 I di1 by dt plus M di2 by dt. Here if you apply a KVL here, V2 applied given overall voltage, and I2 is the flowing current. So L2 I2 di2 by dt, as here d should be written, okay, plus M di1 by dt. If in the second case, if you take here the dotted term, the first coil is at the beginning, in the second coil the dotted terminal is at the end of the coil. So when the current enters into this dotted terminal, this circuit is rewritten in this form. This circuit is redrawn like this. Here this L1 is same as the current is entering in the dotted terminal, so the other side of the dotted terminal will be positively given. So while drawing the first coil, the effect of coil 2 is drawn here. So I1 current flows here as it is the L1 is drawn, and here the current in this coil is leaving the this dot is drawn at leaving time. So at the leaving time, if you see the coil 1, the dotted terminal will be negatively signed. So top will be negative, bottom will be positive. So this is written like this. It is an independent source with minus on the top and positive on the bottom. If we consider coil 2, L2 is same, but while coming to mutual inductance, the effect of current 1 is taken and will be placed here. So the current is in this coil, the current is entering the dot. So if it enters the dot, the coupled value at the negative, it is at entering the dot, it will be positive. So if we draw like this, at the dotted position it should be written as positive. So at the bottom I wrote positive and the starting will be negative. So if you apply KVL in this loop, then it will be V1 L1 di1 by dt minus M di2 by dt, and similarly this equation. And the case 3 is if a coil, if the current leaves the dotted terminal, the other side dotted terminal will be negatively assigned, and the equivalent circuit is drawn here. Similarly, here the L1 is common. This mutual inductance is due to the coil 1 mutual inductance. So we will consider I2. Here I2 is entering the dot, so the dotted position will be negatively assigned. So if you see like this, and the dotted sign will be, dotted position will be negatively signed. As the current is entering, the dotted terminal will be positively assigned. So bottom will be positive and the top will be negative. Here while going to the coil 2 equivalent circuit, the mutual inductance is due to flowing of current I1. So I1 is leaving the dot. So the dot position will be negatively assigned. So top will be negative, bottom will be positive. That I have written here. And if you apply the KVL, the equation will be looks like this. And here both coil 1, coil 2 are leaving the dot. So if the equivalent circuit is drawn like this, if I1 is leaving the dot, here L1 is common, so mutual inductance due to current I2. So this I2 current is leaving the dot, so the dot position is negatively assigned. So bottom is negative, top is positive. Similarly for the coil 2, the mutual inductance is due to current I1. So the current I1 is leaving the dot, so the dotted portion of the second coil is negatively assigned. So bottom is negative, top is positive. So top is positive, bottom is negative. If we apply KVL equation, total voltage is equal to sum of all the drops, that is V1 di1 by dt plus M di2 by dt. and V2, if you apply KVL here, then L2 dI2 by dt, here it is positive, so we will get more clarity if we take an example. This is a sample example. In this 4 Henry, 5 Henry and 3 Henry inductors are connected in series. The mutual inductance between them is 2 Henry and 2.5 Henry. Here in this inductance this inductor will containing two effects. One is self-inductance and one is mutual inductance caused by 2 Henry. This 5 Henry consists of self-inductance and two mutual inductance. One is due to coupling with 2 Henry and another is with 3 Henry. So two voltage drops can be seen here. For 3 Henry, there is one mutual inductance between 3 and 5, that is 2.5 Henry. So if we convert to the equivalent circuit, so the self-inductance is written like this, and for mutual inductance which is connecting to 5 Henry, this mutual inductance is due to the current flowing in 5 Henry. So in 5 Henry the current is entering in this dot terminal. So at this position it is considered as positive one. So at the end it is positive, at the beginning it will be negative. So here also at the end it is positive, at the beginning it is negative. So now 5 Henry. 5 Henry is connecting with 4 Henry and as well as 3 Henry. So first we will write with 4 Henry. So the mutual inductance caused by current in the 4 Henry is, as the current leaving the dot, so this starting point will be negatively assigned and next will be positively assigned. So it is negative and positive. This is self-inductance as it is 5 Henry, and this mutual inductance here, this which is linking with the 3 Henry. As linking with the 3 Henry, the current is entering in this dot. So the current is entering here. So the point on the 5 Henry is positively assigned. So top is positively assigned, bottom is negatively given. Top is positively given, bottom is negatively given. That is 2.5 Henry. And the self-inductance 3 Henry is written as it is. And the mutual inductance due to 5 Henry is written here, that is 2.5. The sign conversion is this is due to current flowing in the 5 Henry. So the current entering the dot terminal. So entering means the value should be, first beginning will be positively assigned, next will be negatively given. So it is positively given and negatively assigned. So if you apply KVL, input voltage is equal to sum of all output voltages or output drops. So 4 di by dt minus, as it is a starting sign, we will take it as minus 2 Henry di by dt minus 2 di by dt, as it is a plus 5 di by dt plus 2.5 and plus 3 and plus 2.5 dt. Overall the value will be V is equal to 13 di by dt. Inductive coupling in series circuit. As we know, it is two inductors connected in series, then the equivalent inductance will be L1 L2 plus 2M. You can see this equivalent diagram. Similarly, if the dot is placed here and another dot is placed at the leaving end, then the equivalent inductance will be L1 plus L2 minus 2M. So how I drawn this equivalent circuit is, L1 is as it is, mutual inductance as it is, this mutual inductance is due to the current in this inductor. So as it is leaving and leaving the dot, so the beginning point will be negatively assigned. So negatively assigned. So L2 is same. For mutual inductance that is caused by the L1, the current is entering here. The dotted terminal will be inductive coupling in parallel circuit. As we are discussing, it is in commutative way. So the equations I have given here, you can go through, and I have this document will be placed in the description section. So you can go through these equations, and the final output only the important thing. So the equivalent inductance for inductive coupling parallel circuit is L1 L2 minus m square by L1 plus L2 minus 2m. If the same with the dotting at different polarities, at first coil with the starting entering end, and another coil the dot is placed in the leaving end, then the equivalent inductance will be L1 L2 minus m square by L1 plus L2 plus 2m. From it's just two small questions. The first question is, as we seen this a series coupled circuit, what is the equivalent inductance? The answer is L1 plus L2 minus 2m. For this circuit, you can try on your own, as one example is discussed on the above. What is the effective inductance of circuit across the terminal A and B? The answer is 11 Henry. I will be just giving the hint. You solve the question. First, you split this equation, this circuit into considering mutual inductances also. One is 4 Henry. As this 4 Henry is linking with 5 Henry inductor and 6 Henry inductor. As there is a two ways, one with 1 Henry, another with 3 Henry. Linking 4 Henry with 5 Henry is given as M12. Linking with 4 Henry with 6 Henry is M13. Similarly, the mutual inductance which is linking 5 Henry to 4 Henry is M21, and 5 Henry which linking with 6 Henry is M23. Similarly for the same, the third inductor which is linking to both first inductor and second inductor is M31 and M32. The values and the sign of the inductor I have discussed and I have written here. You can, if you go through, it will be understanding it. First one I will be explaining. M12. M12 is the inductor. From 4 Henry the current is entering. So at the 5 Henry dotted terminal is positive. So here mutual inductance which is caused by the current flowing in 5 Henry. As the current is leaving the dotted terminal, though this dotting point will be negatively assigned. So starting is negative, next is positive, that is 1 Henry, M12. Similarly for M13, M21, M23, M31 and M32, and finally the inductor circuit is written like this. If you apply equivalent inductance, then the overall inductance value will be 11 Henry. Thank you.